Good day, everyone. So, this is the first part of discussion 2.6 logarithmic functions and equations. Okay, let's start. Let b be a positive real number not equal to 1. If b raised to y equals x, then the exponent y is called the logarithm of x to the base b, denoted by y equals log of x base b. So based on this definition, you can think of the logarithm of x to the base b as the exponent in this one right here, b raised to y equals x. One good thing about this logarithm is that we can connect this with your exponential functions, since if you will look at the definition, we derive the logarithm from an exponential equation. So let's consider these two functions, f of x equals b raised to x and g of x equals log of x base b. And let's try and determine what is f of g of x. So we have here that f of g of x is b raised to, so x will be replaced by this g of x right here. We have b raised to log of x base b. But log of x base b, based on definition, is y. And we have b raised to y equals x. So this one right here will become b raised to y, which is equal to x. So as you can see, the composition of f and g is equal to x. And based on our discussions last month, this means that f and g are inverses of each other, are inverses of each other. So the inverse of your exponential function is actually this logarithmic function right here. And therefore, we have the following properties. The properties which arise from the logarithm being the inverse of your exponential function. So first, recall that the domain, so if you have f of x equals b raised to x, where b is greater than 0 but b is not equal to 1, recall that the domain of this one is R, and the range of this one is the open interval 0 to positive infinity. Furthermore, recall that the domain of your inverse function is the range of the function itself, and the range of your inverse function is the domain of the original function. But remember, just like what we have said, the inverse of your exponential function is the logarithmic function. So the domain of your logarithmic function is the range of f, which is 0 to positive infinity, while the range of your logarithmic function would be the domain of your exponential function, which is r. Second one, this is a property pertaining to the graph of your logarithmic functions. Since the logarithmic function is the inverse of the exponential function, its graph is just the graph of your exponential function reflected about this line, y equals x. And so we have the following properties here. First one, your logarithmic function has no y-intercepts. Why is that the case? So if you recall our exponential functions, we have this one right here, or this one right here. As you can see, in both cases, they are asymptotic about the x-axis. And so, if we reflect them with respect to y equals x, what we will produce are these two graphs below. So first one, we have the graph of y equals log of x base b, where b is greater than 1. As we can see, as we approach the y-axis, it just goes down but not really touch this line right here. And similarly, for y equals log of x base b, where b is in between 0 and 1, as we go to 0, the function just goes up, but it doesn't actually cross this line. Therefore, your logarithmic functions do not have y-intercepts. Next, we have g of 1 equals 0. So log of 1 0. And we have g of b equals 1. So that means log of b base b equals 1. And lastly, if b is greater than 1, then the logarithm of x base b is greater than 0 for x greater than 1. So as you can see here, it's positive. And log of x base b is less than 0 if x is in between 0 and 1. So as we can see here, log of x base b is negative. However, if b is less than 1, the equalities change. So if x is greater than 1, the logarithm of x base b becomes negative. But if x is in between 0 and 1, the logarithm of x base b is greater than 0. Some terms that we have to remember. First is the common logarithm of x, which we denote as log of x. That is the logarithm base 10, while the natural logarithm of x, written as ln of x, is logarithm base e. So as you can recall from our discussion about exponential functions, e is the Euler's number. Then lastly, since the logarithm and the exponential functions are inverses of each other, we have the following. First, log of b raised to x, base b equals x. However, we have to be careful for the values of x. If you can recall, f inverse of f of x equals x for all x in the domain of x. So in this case, the inner function is b raised to x, whose domain is the set of all real numbers. So this equality here would be true for all x in the set of all real numbers. However, for the second one, b raised to log of x base b equals x, this will only hold for the domain of this one. But just like what we said, the domain of this one is the open interval 0 to positive infinity. Okay? So let's have some examples. First one, we want to convert these exponential equations into logarithmic form. So how do we do that? Recall that we have b raised to y equals x. B raised to y equals x, which we said is equivalent to log of x base b equals y. So looking at these two equations, what happens to b? So initially, b is the base of your exponent, but now it becomes the base of your logarithm. Second one, the exponent y becomes the number at the right side of the equation. And lastly, this x at the right side of your exponential equation becomes the argument of your logarithmic function. So to convert from exponential to logarithmic, the base becomes the base of the logarithm, the exponent becomes the number at the right hand side, and this number at the right hand side becomes the input of your logarithm. So let's try letter A. For letter A, we have 3 raised to 5 equals 243. So just like what we said before, the base of your exponent becomes the base of the logarithm. The exponent becomes the number at the right hand side. And this number at the right hand side becomes the input of your logarithmic function. So we have here log of 243 base 3 equals 5. Next example, letter B, 2 raised to negative 7 equals 128. So same thing, you have your logarithm. The next, the base here, which is 2, would be the base of your logarithm. Then this number right here, negative 7, becomes the number at the right hand side. And lastly, this number at the right hand side becomes the input of your logarithmic function. So that's 1 over 128. I hope you kind of get the hang of it already. Let's try letter C this time. We have 81 raised to 1 over 4 equals 3. So same thing. The base of your exponent becomes the base of the logarithm. The exponent becomes the number at the right hand side. And lastly, this number at the right hand side of the exponential equation becomes the argument of your logarithm. Okay, so let's proceed to the next set of examples. For number 2, evaluate the following. So let's go back first to this one. To evaluate logarithms, what we want to do is to convert them into exponential form, since we already know how to solve exponential equations. So what we can do is equate the logarithm to a certain variable, then convert it into its exponential form, and let's apply what we know in solving exponential equations. So let's try it for letter A. So first step, we can let's say y to be equal to log of 1 over 25 base 125. To convert this into exponential form, so babaligtarin lang natin yung process. This base of the logarithm becomes the base of the exponent. This y right here becomes the exponent. And the number 1 over 25 would be at the right side. So we have 125, the base of the logarithm, raised to y, this one will be your exponent, equals this number inside your logarithm, 1 over 25. And now let's apply what we know about solving exponential equations. So what we want to do is write these two numbers as exponent with the same base. So first, 125, we can write this as 5 cubed raised to y. And this number right here, 1 over 25, could be written as 25 raised to negative 1. But 25 is just the same as 5 squared. So we can write this as 5 cubed raised to y equals 5 squared raised to negative 1. And finally, by the loss of exponent, we can multiply these numbers right here. So we have 5 raised to 3y equals 5 raised to negative 2. And as you can see, we have two exponents here with the same base. So that means we can equate their exponents. So we have 3y equals negative 2, which finally would give us y equals negative 2/3. But again, what is y? Based on our very first step, y is log of 1 over 25 base 125. So this means that log of 1 over 25 base 125 is equal to negative 2/3. I hope this example is clear. So the general process, we just let this one to be a certain variable y, then convert into exponential form, and finally apply what we know about solving exponential equations. Let's do letter B. So for letter B, we have log of 1 over 27 base 3. So same process, we can let's say q be equal to log of 1 over 27 base 3. Then converting this one into exponential form, this one goes to the base of the exponent, this one would be the exponent, and this one would be the number at the right hand side. So we have 3 raised to q equals 1 over 27. So once again, 3 to q equals 1 over 27. Next, let's solve 3 raised to q equals 1 over 27. This one right here could be written as 27 raised to negative 1. But 27 is just the same as 3 cubed. So we can write this as 3 raised to q equals 3 cubed raised to negative 1. And finally, by the laws of exponents, we can multiply them. So we have 3 raised to q equals 3 raised to negative 3. Since we have two exponents here with the same base, we can now equate their exponents. So we have q equals negative 3. Therefore, since q is this one right here, we have log of 1 over 27 base 3 equals negative 3. Okay? Let's proceed to the third example. So here we have ln e squared, which by definition is just the same as log of e squared base e. So same thing, we can let's say, I want to be quirky, so let's say a quarter note. Let quarter note be equal to ln of e squared, which is just the same as log of e squared base e. Then same thing that we have been doing a while ago, we can convert this into the exponential form. This one would be the base of your exponent, and this number would be at the right hand side. So we have e raised to quarter note equals e raised to 2. And finally, since we have the same base, we can equate the exponents. We have quarter note equals 2. Therefore, ln of e squared equals 2. Okay? So now I hope you are getting the hang of it in evaluating logarithms. Lastly, let's evaluate this one right here. Log of 64 times 512 base 2. As you can see, we have a product of two numbers here. So it might be tempting for us to multiply them. However, let's see first if we can exploit some stuff that we know about exponents before multiplying them. Maybe we can simplify things further. So same thing as we have been doing a while ago. We can let's see, I want to use alpha this time. Let alpha to be equal to log of 64 times 512 base 2. Then, so let's convert this into exponential form. This one would be in the base. This one would be the exponent. And this one would be the number at the right hand side. So we have 2 raised to alpha equals 64 times 512. However, if you can recall, 64 is just the same as 2 raised to 6, and 512 is just the same as 2 raised to 9. So we can write this as 2 raised to alpha equals 2 raised to 6 times 2 raised to 9. And by the laws of exponents, since you have the same base, multiplying them would just be the same as copying the base and adding their exponents. So we have 2 raised to alpha equals 2 raised to 6 plus 9. And so we have 2 raised to alpha equals 2 raised to 15. And finally, since we have the same base here, we can equate their exponents. We have alpha equals 15. And so, since alpha is this one right here, we have log of 64 times 512 base 2 equals 15. And this is the last example for this discussion. So please check the second part of our discussion so that you can learn the properties of logarithms and how to solve logarithmic equations. So thank you everyone and keep safe.